mechanical force per unit area. This is one of the important expression. The question can be asked, derive the expression for mechanical force per unit area. For generally 3 marks this question can be asked in the exam. So let's start with the diagram to find out the mechanical force. We'll consider the conductor of any shape. This type of conductor of any shape. Let sigma be the surface charge density. Surface charge density means is the charge per unit area. Okay. Now charge is distributed over the surface in this way. Okay. Now we'll consider a small surface area ds. Okay. Here we'll consider small surface area ds. This is the small surface area ds. Now see, we have divided this entire surface into 2 parts. Which are the 2 parts? This is the one, that is ds is the small surface, and this remaining surface. Okay, so some charge is there. See, entire charge density, surface charge density is sigma overall on the surface. Now we have here the 2 surfaces. One is this small surface and this is the remaining surface. Now charge is there on the small surface as well as charge is there on this remaining surface. Okay. Because of the charge there is an electric intensity. So here electric intensity due to this small surface charge on this small surface area as well as electric intensity due to the charge on this remaining part. Okay. So E1 and E2 like that way we are going to take. Now we are going to consider the 2 points. One is just outside and one is just inside. So here we will take point which is just outside this conductor and here just inside. So let this point is A and this point is B. Like this way the 2 points we have taken which is just outside and just inside. Now the electric intensity due to the charge on this surface ds, let it is E1. So what I am taking here, E1, this is the electric intensity due to charge on ds. On the small surface area ds, whatever the charge is, due to that this electric intensity E1 is produced. And then E2, it is the electric intensity due to the charge on this remaining surface. Okay, so this is the electric intensity due to charge on remaining surface. Okay, now we'll show the direction of this electric intensity is E1 and E2. Okay, this is very important to know what is E1 and what is E2. Once again I tell you that E1 is the electric intensity due to the charge on ds. ds पे जितना चार्ज है उसके कारण E1 इलेक्ट्रिक इंटेंसिटी होते हैं और E2 is the electric intensity because of the charge on this part, remaining part. Okay. Now the direction of E1 and E2 I am showing. The direction of E1, that is the electric intensity due to the charge on ds, that is outside as well as inside. So I am showing the direction for E1. It is pointing outward as well as inward. Then the electric intensity due to the charge on this remaining surface, that is E2, E2 is pointing only in the outward direction in this way. This is E2. Alright. Now at point A, that is A point is just outside. Now see the outside, the direction of E1 and E2. How they are? The direction of E1 and E2 are in the same direction. Therefore, the resultant of E1 and E2, I can show like this way. This is the resultant of E1 and E2, which is equal to E1 plus E2. I am taking here plus E2 because their directions are same. E1 and E2 directions are same for a point which is just outside, and therefore I am taking that E, it is equal to E1 plus E2. Now say inside the conductor. Inside the conductor, E1 and E2 directions are opposite, like this way. And therefore, inside the conductor, the resultant intensity E bar, it is equal to E1 minus E2. But we know that inside the conductor electric intensity is always 0. So resultant is 0. It is equal to E1 minus E2. Okay, this is about the diagram. And now we'll see the derivation part of this. First we'll consider inside the conductor. You know, inside the conductor, first point we'll write inside the conductor. Okay, inside the conductor we know that resultant intensity is always 0. There is no electric field inside the conductor. Okay, and the direction of E1 and E2 are opposite, therefore the resultant is E1 minus E2. Therefore we can write E1 bar minus E2 bar, it is equal to 0. And therefore we can write E1 it is equal to E2. Equation number 1. This is for inside the conductor we have seen. Now outside the conductor, the second point we'll see outside the conductor. Now outside the conductor you can see here the direction of E1 and E2 are same, therefore the resultant is addition of these two, vector sum of these two, and therefore E bar it is equal to E1 plus E2. These are the vector quantities. Okay, now E1 and E2 are equal from equation number 1. So I am putting here the value of E1 as E2. Therefore we will get E2 plus E2. Resultant intensity in magnitude we can write E is equal to E2 plus E2, that is equal to 2E2. So we got here resultant intensity, the magnitude of resultant intensity at point A, which is just outside, it is equal to 2 times E2, and therefore E2 it is equal to, therefore we can write E2 it is equal to E upon 2. Okay, now what is E? E is the electric intensity at point A, that is the point just outside the conductor. Okay, and we know that we have seen the third application of Gauss's theorem, that is electric intensity at a point just outside the conductor of any shape. It is given by the equation sigma upon epsilon or sigma upon epsilon naught k. So that value we are putting here. Therefore we can write this value of E is sigma upon epsilon naught k divided by 2. So that can be written as sigma divided by 2 epsilon naught k. This is the value of E2, equation number 2. Okay. We got now here the value of E2, that is the electric intensity due to the charge on this remaining surface at point A we got. Now we are going to find out the mechanical force per unit area. Okay, force it is equal to, we know that electric intensity in the 11th standard you have studied that electric intensity it is defined as force per unit charge, F upon Q, it is equal to E. Therefore F it is equal to intensity into charge, and the same expression we are going to use here. Therefore mechanical force F it is equal to intensity into charge. So intensity is E2 into charge on ds. Okay, so it is equal to intensity E2, that we can take the expression from equation number 2, that is sigma upon 2 epsilon naught k, and charge on ds. We know that the surface charge density is sigma. Here we have taken the sigma is the surface charge density, and sigma it is equal to q upon ds. Therefore q it is equal to sigma ds. That value will substitute there. So sigma upon 2 epsilon 0 k into sigma ds, it is equal to sigma into sigma, here sigma square divided by 2 epsilon naught k into ds. This is the mechanical force acting on area ds. We are going to find out the mechanical force per unit area. So take this ds this side. So what we will get here, that is F upon ds, it is equal to sigma square upon 2 epsilon naught k. This is the expression for the mechanical force per unit area. If we denote here force per unit area, if we are using here the small f letter for it, then one can write the expression like this way. Therefore, F it is equal to small f, this is the letter used for mechanical force per unit area is small f, it is equal to sigma square divided by 2 epsilon naught k. So this is the force formula. Mechanical force per unit area formula is sigma square upon 2 epsilon naught k, where sigma is the surface charge density, that is nothing but charge per unit area, and here epsilon naught, this is the permittivity of the free space, and k, that is the dielectric constant, and it remains 1 for air, and for any other medium the k value will be given. So this final expression we got for mechanical force per unit area. We can extend this formula by substituting the value of sigma. Okay, in the exam if it is asked, then only you will continue.